Hello, statisticians. In today's lesson, we are focusing on measures of spread and percentiles. In the last lesson, we started to explore the idea of the American dream, that the next generation can do better than those who came before. And we said that a key aspect of achieving the American dream is through home ownership. And keeping in mind that a roof over your head is something that we all want, why does it matter whether you rent or buy your own home? Some people think renting is nice because you get to have someone else take care of any repairs that come up. But financially, rent goes to the owner of the home. By owning your home, even if you are paying a mortgage, it means that some portion of what you pay is an investment and can eventually build wealth. In the previous lesson, we saw that it may be harder to buy a home for your generation than for your parents or for your grandparents. Why should we be concerned about that? That raises a new version of our continuing key question. Is the American dream still alive? With that question in mind, let's move into our notes. We'll be working on 3 things today, beginning with measures of spread. And within that topic, we'll be looking at 3 specific measures. The first measure of spread we will discuss is the standard deviation. The standard deviation measures the typical distance of the data values from the mean. To best demonstrate the concept of standard deviation and to really understand what this means, it's best to look at a simple example. These 2 simple data sets each have 4 data values. The first set has 4 values that are less spread out from one another. And the second data set has values that are more spread out from one another. Recall that the standard deviation is the typical distance of the data values from the mean. If we calculate the mean for both of these data sets, we will get a value of 7 for both. And they're symmetrically distributed from that center value. Now, we can look at the distance of each data value from the mean. In the first set, there is a data value of 8, which is 1 unit above the mean. And there's another value at 9, which is 2 units above the mean. There's a value at 6, which is 1 unit below, and a value of 5, which is 2 units below the mean. So typically, all the data values are somewhere between 1 unit or 2 units away from the mean. So we expect the standard deviation to be a number somewhere between 1 and 2. We'll do the calculation in a moment. Similarly, for the second data set, we are going to expect the standard deviation to be somewhere between 2 and 3. Now, we use technology to get these data values of a standard deviation of 1.83 and 2.94, and we'll come back to that in just a moment to see where those numbers came from. Just like with mean, we've got some symbols for standard deviation. We use a lowercase sigma to represent the population standard deviation and an S to represent the sample standard deviation. In order to calculate the standard deviation by hand, it's a very long and tedious progress. We're typically going to be using CODAP and other statistical tools to do those calculations for us. But first, let's take a look at how it works. That way you can make sense of it and interpret it on your own. So here's the formula. It's a bit intimidating, but it's not magic. It's math that you know how to do. So let's start with the symbols within the formula. We know that the S, that's what we're calculating, is the sample standard deviation. The N is the sample size. It's the number of data points that you have. In this case, it's a 4. The X sub I, we remember from our mean formula, that is the individual data values. So in this case, sometimes it's a 5 or a 6 or an 8 or a 9. Those are the 4 data values that we have. The X bar, that's the mean. In this problem, we calculated it earlier. That was a 7. Remember that the capital sigma means we're going to be adding something. So here's what we're going to do. We're going to follow the order of operations and come up with our value. So we're going to take each individual data value, and one at a time we're going to subtract it from the mean. So we'll do 8 minus 7, and then 9 minus 7, and then 5 minus 7, and then 6 minus 7. Each of those individual data values subtracted from 7 gives us these 4 values. Some of them are positive, some of them are negative, because some of them are above or below the mean. Then the next part of the formula shows that we're squaring something. So we're going to take all of those numbers and square them. So technically it didn't matter that some of them were negative, because those negative numbers squared are going to end up being positive values. Next, we've got that capital sigma. Remember, the capital sigma means that we're going to add all of those values together. Next up, we have 1 over n minus 1, and we're multiplying it by the value we had before. Remember, n is 4 in this case because we have 4 data values, and rather than multiplying by something, 1 over n minus 1, that's the same thing as dividing by n minus 1. So the sum of the values was 10. We're going to divide by 4 minus 1, which is the same thing as dividing by 3. And so far, that simplifies to 3.33. Next up, we're taking the square root of that, and that's where we get the 1.83 for the standard deviation. Now, that was not so bad, but you can imagine that it gets complicated when you have larger data sets. So we're going to be using CODAP and other technology tools to do this work for us. You just need to understand what standard deviation means and how to interpret it. So remember that standard deviation means what is the typical distance from the mean. So all of these 4 data points, they typically vary by 1.83 units from the mean of 7. So let's go back to our context from before. The standard deviation of these 12 home prices is 9,688. That means that the home prices typically vary by $9,688 from the mean. Now our next measure of spread is range. You've probably seen this one before, and thankfully it's not quite as complicated. It's a bit simpler. We're just doing the maximum value minus the minimum value. And our range for this data set is $33,090. Our interquartile range is our third measure of spread, abbreviated as IQR. Now you'll remember from the last section of notes, we found the median, or Q2, and you'll find Q1 and Q3 to calculate the IQR in a similar manner. Q1 and Q3 are just the medians of the first and second half of the data. So first you'll find the lower half of the data, you'll find the median of that value. There are 2 numbers in the middle, so you'll find the median of the lower half, find the average of the 2 values in the middle, and that gives you Q1 or quartile 1. Do the same thing for the second half of the data, and that gives you Q3. And the formula for the interquartile range, remember, is to find the difference of those values. So our Q3 minus Q1 gives us an IQR of $10,300. So the difference between those is our IQR. Now next up, we're going to move on to percentiles. A percentile has a definition of being the percent of data values that are less than or equal to a certain value. Now just a note before we move on that you may see a different definition of percentile in different locations. For the purposes of our class, we're using the definition of less than or equal to, but in the wild, you may see the definition of strictly less than. Just be aware of that. Again, we are using less than or equal to for our course. So an example of this, we might be asked what percentile is the home in our data set that sold for $36,700. So that's this home right here. It's the second highest sale price. And recall that percentile is the percent less to or equal to a value. So we're going to count all the homes that sold for prices less than or equal to $36,700. Those are all the homes that are highlighted here. So in total, there are 11 out of 12 homes in our sample that meet this criteria. So 11 out of 12 is 0.917 or 91.7%. That means that the home that sold for $36,700 is at the 91.7th percentile. If we go back to our quartiles, you might notice how it sounds similar to percentile, and that's because those are related. So the first quartile is the 27th percentile, and the median, also known as Q2, is at the 50th percentile, and Q3, the third quartile, is at the 75th percentile. These are going to be pretty handy for you to know that these are mapped to each other, and they'll help you with some calculations. Okay. Last up, we're going to talk about CODAP and give you some time to explore a little further from what you did yesterday. So again, in this lesson and in the last lesson, we covered a lot of summary statistics and how to calculate them. Although it's conceptually helpful to see and practice calculating these measures of center and spread by hand, most statisticians use technology to find these values from real data. You'll be getting the opportunity to use CODAP to explore all of these measures a bit more. Keep in mind that as you go through the activity using CODAP, to consider what these measures tell you about the data beyond just a formula and a number. Before you head off to do that, let's take a look back at our discussion question and wrap up. So our home buying rule of thumb is that it's best to avoid buying a home that costs more than 3 times your income. That way, you are not buying a home that you cannot afford. In 1970, the median annual income for a young adult, which is someone 25 to 34 years old, in the US was $9,853. And the median home price, as we saw in our data set, was $22,300. That means the median home price was about 2.3 times the median income for this age group. Because that falls well below the 3 times income rule, a young adult making the median income could reasonably expect to afford to purchase a median priced home. That means young adults starting in the job market and starting to get into their careers, that's good news. They could expect to afford a home. Now, in 2024, partly due to economic growth and partly due to inflation, the median household income among similarly aged adults raised substantially. It's now $90,100. Seems like good news until you see the new median home price is $423,000, which is also substantially larger. It's 4.7 times larger. So that doesn't meet the 3 times your annual income rule. It's a little out of reach. So that brings us to our discussion question. If a 30-year-old is making the median income for their age group, how much would their income need to increase to be able to afford a medium-priced home? And here's an additional challenge question if you're up for it. If it takes them 5 years of annual increases to reach that salary, and home prices continue to increase by 1% per year, how many more annual increases would it take for them to be able to afford a new medium-priced home? So take a moment, jot down your initial thoughts about these questions, and be ready to discuss in class. That's it for today's statisticians. We'll see you next time.